In this video, I'm going to summarize the midterm exam and give you the solution. You can compare your grading with the solution, and if there's anything wrong, you can contact me through Microsoft Teams. Okay. So the raw scores is the score written on your exam. So the range is 47 to 95 with a median of 73. Okay, and on the in the top right corner, this figure shows the midterm raw score distribution. Okay, for your reference only. And to give you a better grade, 10 points will be added to everyone's raw scores as your adjusted midterm score. And the adjusted midterm score will be used to calculate your midterm letter grade and also later for your final letter grade. For the midterm letter grade, homework will contribute 15%, then quiz 5%, and the adjusted midterm will contribute 80%. And the attendance is not counted for the midterm, but will be counted for the final. Okay. The lower right corner, this figure shows the midterm letter grade distribution. Okay. Now let's go to the solution. Get my laser pointer. Okay. So for the first problem, problem 1a, you know the average thermal power of one field pin, which is 159 watt per centimeter. You also know the total length of this field pin, and the question asks for the total thermal power of this field pin. So this question is fairly simple. You just use the power per unit length, Q prime average, times the total length of the field pin. So you get the total thermal power of one field pin. Okay. This is problem 1a. Problem 1b. You know the inlet and outlet coolant temperature, and you want to calculate the coolant mass flow rate for this field pin channel. Okay, so the coolant will be used to remove the heat power from this field pin, and you want to calculate the amount of coolant needed per second. Okay, you also know the CP. And the equation is shown here. Okay, so you have your m dot, that is the coolant mass flow rate, P thermal, that is the thermal power of one field pin, Cp is the specific heat of this coolant, which is given. Delta T is the coolant temperature difference between the inlet and outlet. Then you replace this those variables by the numerical value, okay, and pay attention to the unit. So convert the kilowatt to watt, and everything will be a standard unit. Then you will get the coolant mass flow rate. Problem 1c, you know the reactor thermal efficiency, that is 35%. You want to calculate the waste heat power. Okay, so 35% means that 35% of the heat produced will be converted to mechanical power or electrical power, and the remaining 65% will be the waste heat, has to be rejected to the environment. So the waste heat power is simple, just the P thermal, total thermal power, times 1 minus eta. Okay, then that will be your waste heat power. On this slide, I also show the point distribution. In general, we have the problem either has 5 points or 10 points. For the 5 points problem, the equation will give you 2 points. For the equation, there will be no partial point. So if there's anything wrong in the equation part, you lose the entire 5 points. And there will be no points given. Then if the equation is right, then the second part, numerical value substitution, if there are 5 points, this part is worth of 2 points. Okay, and here I will give the partial credit. So if only one value is wrong, then you get 1 point for the other correct value. The last one is final answer with unit. And for 5 points problem, if the value or the unit is wrong, then you lose this 1 point. Also, the correct answer is answer within 1% relative error. Okay. And the second, the 1B problem is an example of 10 points problem. For 10 points, the equation is worth of 4 points. Then the numerical value substitution is another 4 points. And the final answer is 2 points. Okay. So if the value is right, but the unit is wrong, then you get 1 point for the final part. Okay. Next one, we calculate the average neutron flux. So the average neutron flux is related to the thermal power. So the device has a thermal power of 1 kilowatt. And we'd like to calculate the neutron flux. So for the relationship between the neutron flux and the power, it is shown by this equation. In this equation, the phi average is the average neutron flux we want to calculate. P is the thermal power. W is the heat released coefficient. Okay, heat released coefficient or energy release coefficient. Then sigma F is the macroscopic cross section, and V is the volume. Okay. And we just need to split the sigma F to lowercase sigma F times n. Okay, times n. Here the P is 1 kilowatt, so we used 1000 watt. Then the W is 190 MeV per fission. We need to convert the MeV to joule, so we multiply this coefficient, joule per MeV. Then times the macroscopic cross section, which will be the atomic density, then times the sigma F. Sigma F can be found from the table. Then times the volume of this device. When you calculate the volume, you need to use the physical radius. Okay. So here we have 4/3 pi r cubed. That is the equation for a sphere volume. Then the result will be your neutron flux. The unit will be neutrons per square centimeter per second. The last one determines the center to edge neutron flux ratio. And we have the equation for for you to calculate the neutron flux at any location along the radius, which is shown here. For this formula, I already substituted the lowercase r, that variable, by the capital R, okay, by capital R. So if you set the lowercase r to be the capital R, that will give you the neutron flux at the boundary, okay, because at the boundary the radius will be 10 centimeter. And here the phi c is the neutron flux at the center, that is your maximum neutron flux location. It is a value unknown, okay, value unknown, but it doesn't matter. So this r tilde, again, that is the physical radius plus the actual population distance. Okay. Then go to the next step. You will see that the r tilde will be replaced by 10 centimeter plus actual population distance. Okay. And here this r and also this r, that is your radius at the edge. Okay, at the edge, you get this value. This value means that at the surface of this sphere, the neutron flux is about 22% of the phi center. Okay, of the phi center. So problem asks for the center to edge neutron flux ratio. So we want to calculate the phi center over the phi r. Okay, over the phi r. And this phi c will be cancelled. Then you get 4.6. So it means that center neutron flux is 4.6 times of the edge neutron flux. Okay. Now let's go to the last one. For the last one, it is isotope separation problem. First one, we need to determine the abundance ratio of the product. So the equation is simple and also already given to you. So RF, that is the abundance ratio, will be equal to, by definition, that is the atomic density of the light particle over the atomic density of the heavy particle. However, the problem certainly give you the abundance in terms of weight. So we convert this n to the weight. So here this omega, that is the weight percentage. And this lowercase m, that is the atomic mass or molecular mass, depending on what material you are separating. You need to read the problem. This problem will process the uranium metal. It is no longer UF6 as used in the commercial enrichment plant. Therefore, you will also see that I didn't give you the atomic mass for the F. Means that you need to divide the atomic mass of the uranium-235 and also the 238. Okay, then you get the RF. So this is the feed, and we also have the product. Okay, I have the product. The product is 4% in weight. Then we get a different value. So there will be no point given to the RF. Okay, just to give you the point for the RP, because RF we already show how to calculate that in the class. You can use this value directly, or you can recalculate this one here. Next one is the separation factor alpha of this method. And this problem asks you to determine the actual separation factor based on this separation effect from 0.11% to 4%. If you are using some special equation, those equations will give you the theoretical maximum separation factor for certain method. Those equations do not apply to this problem because this is laser separation method. It is not the gas centrifuge or gas diffusion method. So the alpha is very simple. Just calculate this one from the definition. Okay, so alpha is equal to RP over RF. Okay, so that is 5.8. Next one. If this method is used to produce highly enriched uranium with abundance ratio of 90%, how many stages are needed? Okay. So here it means that if we use this one to continuously increase the enrichment, increase the abundance ratio until it reaches 0.9, how many stages are needed? Okay. So number of stages is calculated using this formula, and RP at this moment will be 0.9, okay, over RF, which is the same value as the problem 3a, okay, over the log alpha. You'll get the 2.7 or roughly 3 stages. And for this problem, I should say that the abundance ratio should be 0.9 instead of 90%. This way may give some misunderstanding. So if the student uses 90% as the weight percentage, I gave the full credit. Okay, because here when we are talking about the abundance ratio, we should not use the percentage, just use the 0.9. Okay. So this will conclude the midterm solution. And if you have any question, feel free to message me on the Microsoft Teams. Okay, thank you.